Hello guys and welcome to the first ever video uploaded by the Chemistry Curiosity Club of SCIE, the Shenzhen College of International Education. Because unfortunately we're not verified yet, this is only a sub 15-minute sample. If you have any advice related to chemistry or video making in general, feel free to type away in the comments section. This video is a sample from our review session for the Canadian Chemistry Contest on the topic of vapor pressure and related equations. So, enjoy! Okay, I have 6 minutes on the clock, 5 minutes actually. I'll try to go through this as fast as possible. I'm not going through this as fast as possible. Okay, so now let's look at vapor pressure. Vapor pressure is basically, actually, before we get on to vapor pressure, let's look at first of all the free energy of gas, right? With state quantities and, PO, this is supposed to be, I still have it correct, this is supposed to be standing for the standard pressure, which is commonly written as P0, but, I have a bad keyboard, that's my excuse. So we're now talking about vapors in an isochoric and isothermal environment. Basically, the volume of the container doesn't change, and the temperature of the container does not change. Why is this important? Let's first of all write out the things in the isobaric conditions, which is the delta U, U standing for internal energy, equal to temperature times the change in entropy, minus the pressure times the change in volume. This is supposed to be standing for work, and this is supposed to stand for heat. Entropy, if you would recall, is heat over temperature. So the heat minus the work done would be the total change of internal energy for the specific system. This is when you have equations like this, it always makes sense to try to interpret it in terms of words to make sense of it, because chemistry is logic. It's supposed to be intuitive. Obviously, sometimes it's not. So if you rearrange this with some mathematics, you get the change in U plus PV minus TS, which is the change in the internal energy, will equal to STT minus VdP, because it's isobaric conditions. There's no change in P, so it simplifies to this. I'm going to try to speed up. We don't have a lot of time left on the clock. Change in U plus PV will, because we are also in isothermal conditions, so temperature equals 0, so we can just cross that nominal out, as well as that one. We'll leave you with the change in internal energy will be equals to the negative volume times the change in pressure. So let's instead rearrange this. We know, in fact, that V is, PV equals nRT. You use the universal gas, use the ideal gas law to rearrange it into like nRT over P, and then you sort of integrate it a bit. So integrate it a bit, and you get Loin P, because this will be equal to negative nRT dP over P. And according to A-level mathematics, when you integrate this, it will be equals to RT Loin P, and you divide the n at the other side. And then you put this into context, because here you have the change in internal energy of the entire sample, and you divide that by the number of moles you have in that sample, you get the free energy, the capacity to do work of the system. So that is how you derive this equation. Delta G equals delta G standard plus RT Loin P. Which basically means that now for gas, you have replaced Q supposedly with P, and that's much easier because it's hard to measure concentrations in gases. But however, it lacks a bit of sense, because we recall that when we were talking about it, chemistry is not about absolutes, it's about change. And so when you're talking about Loin P, what is zero bars of pressure, right? Can you have negative bars of pressure? I don't know. So instead, normally we compare it instead to the standard state. So you sort of like take away, take away RT Loin P standard. And because we have two loins here, you just simply do a division inside the bracket of P and P standard, and you get this equation. It's simple AS mathematics. It should be easy to grasp. It's basically logarithms. And that is how you get, the free energy, Gibbs free energy for gases, the gas state. Normally we talk about liquids, now you get the gas state. Okay, let's move on. If you have things immediately afterwards, feel free to leave. We'll upload it, I hope. But afterwards, things will be fine. Okay, that's that. Okay, so now we're going to attempt to derive delta H standard of vaporization, along with, and why this ratio here, this logarithm, is very, very important. Let me just open up my notes. There we go. Okay, so originally we have for, if we are to measure the free energy of gas of a solid, we have delta G for a liquid solid. Liquid will, I think that's about it. It should equals to delta G of vaporization. I'm not sure. Let me check on this real quick. It's a lot of stuff to remember. Okay. Okay, so normally what we have, I'll give you simpler explanations because the harder explanations are on adkins, which I couldn't really strictly remember and I don't have time for now. So I'll give you the simpler one. So normally what we have here is delta G standard equals to delta H standard minus standard. So if you have using the equation that we just derived for the free energy of two gases, right? If you have, so if this is, I don't know, free energy of vaporization or whatever. If you have two gases, you have originally at, I don't know, standard states, in room temperature, you have one vapor pressure. But as we heat the whole thing up, it will have a different vapor pressure. So if you will recall, we have delta G. I think it's this will equals to negative RT. Excuse me, got the side wrong. Will equal to RT10 So when you have two different temperatures, you just simply subtract the two states from one another. So for example, you have Q1 minus, I should be using standards here actually. Whatever, you get the idea. This is the rough reduction, so you instead have, because you're doing this deduction here, it will be RT moy of P1 over P standard. Let's do that. Minus moy of P2 over P standard. Okay. And because of logarithmic mathematics, this is yet another fraction. These two cancel out. You put P2 on the bottom, and therefore the free energy will give you the equation of RT1 of P1 over P2. And this is basically what you use to sort of like derive the ratios of two species derive the ratios between the vapor pressure at two different temperatures. So when the question asks you, what if we heat it up, what would be the vapor pressure then? Or after we heat it up, what would be the ratio of gaseous water to liquid water? You can use sort of this change in pressure and equate it with another equation, which is to find the equilibrium constant. So this is what you can yet again use to find how much of it has turned to gas at different temperatures, at different pressures. This is also what you can use. Okay, so what about the enthalpy of vaporization then? In enthalpy of vaporization, I don't want to say this, but you equate this to this, you divide by RT, and then you can just get the whole thing. Dare I say that? For example, now we have floating P1 over P2. So if you do that subtraction, you should get, because we are dividing by RT over here, right? And so temperatures cancel out. However, for this R here, the change in entropy is always constant, no matter the temperature. We assume that. We are allowed to assume that at our level. So when you're subtracting the two free energies, you're just that's a constant. So it just basically cancels out. So instead, you have if you divide by RT at this end, you have instead, I believe, delta H standard over R 1 over T1 minus 1 over T2. I believe that's correct. So because this is basically equal to that, we have divided by RT in this expression. We cross out the RT. So this expression here is now equal to going P1 over P2. So that is how you relate the change in enthalpy of vaporization. So that is how you relate the enthalpy of vaporization to temperatures and the ratio of the vapor pressures.